All right, we are in our last section of chapter 9, and some of this is going to sound kind of familiar. So we've talked about Taylor polynomials and Maclaurin polynomials, and we've talked about their nth terms and the patterns for the coefficients of each term. Like each term has an nth derivative of f evaluated at the center divided by an n factorial, and then it's multiplied by whatever x minus c to the n is. So now we're just going to officially look at this Taylor polynomial as a series. So we've been looking at power series. In 9.9, every power series we had wasn't necessarily built like this, right? We didn't always have factorials. Power series were just series whose terms were powers of n. Sometimes they were Taylor series, sometimes not. Okay, so now we're strictly looking at Taylor series and Maclaurin series. So again, this setup should look familiar to us. Maclaurin is just a special Taylor series centered at 0. And remember, the way to form a Taylor polynomial was to just keep finding successive derivatives a set number of times. And so now, instead of saying, okay, we're going to find the 5th order Taylor polynomial to approximate f of x, we're going to try to find the Taylor power series, not to approximate f of x, but to be equal to f of x on whatever the interval of convergence is. So now we're going to be looking at however many derivatives we need to look at until we can find a pattern to figure out what is that nth term so that I can write out a series. The remainder for a Taylor series, that Lagrange error, is still the same. So the remainder is less than or equal to the n plus 1th derivative evaluated at z times x minus c to the n plus 1 over n plus 1 factorial. Remember, we're still looking for what is this max value. So if we're lucky enough to get just a sine or a cosine of x, not like a sine or a cosine of 2x, we know that max is 1. And if we're not given an approximation value, like if we're just told down here we're going to just find the general remainder at x, then we're going to evaluate at the center. Okay, so practice. Find the Taylor series for f of x equals e to the 3x centered at 0. Now, there is a long way and a short way to do this. Tomorrow is the shortcut, but I want to remind you of the long way because it's not that long, and it's useful if you're not sure if you can use the shortcut or not. It's always best to just put in the work and do this the long way. Okay, so long way today. All right, so what is the long way? If I want to build a Taylor series, it's just like I would be building a Taylor polynomial. I would first say, what is f of x? And what is f of x evaluated at the center? So that's 1. So the constant term here, so far I know the constant term is 1. And then remember we take derivatives. Now you've got a little chain rule going on. The derivative is e to the 3e to the 3x. So the derivative at 0 is just 3. I'm going to write plus 3. This is centered at 0, so it's just plus 3x. Second derivative would be 9 e to the 3x. Evaluated at 0 is 9. So plus 9x squared over 2 factorial. Let's do one more. Third derivative would be 27 e to the 3x. Evaluated at 0 would be 27. So plus 27 x to the third over 3 factorial. There's no need to simplify. Even though 27 over 3 factorial could reduce, we're not going to. So I'm just going to write plus dot dot dot. Now for the Taylor series, I'm trying to get that this is equal to the summation from 0 to infinity of something. So I need to come up with a pattern here. And maybe you can see it, but you can kind of figure it out off to the side too. So how do these coefficients, how do they, at the 0 term, how are they building? Sorry, so this would be 3 to the 0, 3 to the first, 3 to the second, 3 to the third. Okay, so it's pretty safe to say this is 3 to the n. And then we would have, yes, e to the 3x for our nth derivative. But in our Taylor polynomial, we're saying what is the nth derivative evaluated at the center times the center, x minus the center to the n, over n factorial. So we're just trying to figure out, let me go back to this. We're just trying to figure out what is this nth derivative of f at c. Okay, so the nth derivative of f at c is just 3 to the n. Because if you put in a 0 for the x, you get 3 to the n times 1. So my series for e to the 3x is the sum from 0 to infinity of 3 to the n. I'm just going to make this x to the n over n factorial. If you wanted to simplify it, you could. The sum from 0 to infinity of parentheses 3x to the n over n factorial. Now, I don't know if you're thinking ahead to what the short way might be, but this is a really basic one for the short way. I'll just give you a little preview here. What is our power series for e to the x? Just plain old e to the x. This is one of the 4 that we had memorized. It was just x to the n over n factorial. And when I had e to the 3x, I got it to be quantity 3x to the n over n factorial. So maybe you can see what the shortcut's going to be. It looks like it's kind of just a substitution type thing. All right, the remainder. So the remainder of x will be less than or equal to. Now, even though we have f to the n plus 1 evaluated at z times x to the n plus 1 over n plus 1 factorial, remember, in our Taylor series, we have just 3 to the n right here. It's not, there's no x involved in this. So instead of the n plus 1 derivative at z, this is always just, this term right here had always been evaluated at the center, which is 0. So I don't have to think about like, well, what if z is between the center and some approximation? That's not relevant for this particular series. So it's just going to be 3 to the n plus 1 because the nth derivative is 3 to the n. So the n plus 1th derivative at 0 is 3 to the n plus 1. Anyway, so it's 3 to the n plus 1, x to the n plus 1 over n plus 1 factorial. And you could make that 3x the quantity to the n plus 1 if you want it. So here's a new theorem. It's kind of officially putting something that we have talked about previously into a theorem. So if the limit as n approaches infinity of the remainder is equal to 0 for all x in the interval I, then the Taylor series for f, where f of x equals this Taylor series, converges to f of x for all x on I. I added that part in there because it's kind of like, wait, what is this saying? This is just saying, if you can show that the remainder is practically 0, let's think back to our ratio test. When we were doing ratio test and we got like x to the something over a bottom heavy rational expression, we got 0 and we said, oh, this converges for negative infinity to positive infinity, any x I want to put in here. That's all this is saying. If the remainder is pretty much 0 as you head out to infinity, then the Taylor series will be exactly the same as the function f of x. So let's look at, this kind of restates that, this paragraph. So again, if you form a power series with Taylor coefficients, so if you have a Taylor series, then that Taylor series will converge to the function from which it was derived. So it will converge to e to the x or sine x or whatever for all of the values in the interval of convergence. All right, so what do I use that theorem for? Like a little proof like this, and this proof was probably not going to be on the AP test. You'll probably just be saying, find the error bound or find the interval of convergence, but just kind of to look at what this theorem is saying. Let's start with, it says prove that the Maclaurin series for f of x equals sine x converges to sine x for all x. So let's start by reminding ourselves what that Maclaurin series is. It's a series from 0 to infinity of negative 1 to the n times x to the 2n plus 1, it's all the odd powers of x, to the 2n plus 1 factorial. So using that theorem, if I can show what the remainder is for this power series, if that remainder is approaching 0, then the power series is the same as the actual function itself, meaning the two do not stray after a certain amount of time. Okay, so let's do that. What is the remainder? Well, the remainder, let's see, the remainder of x, sorry, is less than or equal to the n plus 1th derivative at z times, we're talking Maclaurin, so just x to the n plus 1 factorial. Now, what is this max value? Remember, the function itself is sine x, so it'll be a sine or a cosine function, positive or negative, but the absolute value of it will be at most 1. So now I know that the remainder is x to the n plus 1 over n plus 1 factorial, because the maximum derivative there would be 1. So now the theorem says the limit as n approaches infinity of the remainder, which is x to the n plus 1 over n plus 1 factorial, that limit equals 0 because it's a bottom-heavy function. You'll have some x raised to a power over a factorial, which is huge. Since the limit is of the remainder is practically 0 in the end, this says that sine x is equal to its power series, or its Taylor series, I should say, for all x in the real number system, or on the interval of convergence, negative infinity to infinity. All right, our final problem for today is to find the Taylor series centered at pi over 4 for f of x equals cosine x. We actually had one similar to this on the quiz. I think I centered it at pi over 3. So how are we going to do this? Well, we can't just build it based off of our Maclaurin series that we have memorized for cosine, because that's a Maclaurin series. It's centered at 0. So the fact that they're only even exponents, that's only happening because you're evaluating at 0. Here we're evaluating at pi over 4. So every term will be accounted for. The first thing to do is say f of x is cosine x. So what's f of pi over 4? Radical 2 over 2. The derivative will be negative sine x. And I'm not going to keep writing this out. I'm going to write this out one more time. The derivative at pi over 4 is negative radical 2 over 2. The second derivative would be negative cosine x. Evaluated at pi over 4 is negative radical 2 over 2 again. Let's take this to 4 derivatives just so we can see what's happening with the signs. The derivative of negative cosine is positive sine, which would give me positive radical 2 over 2. Finally, the fourth derivative will be cosine, another positive radical 2 over 2. This is not really an alternating series. The signs are going plus, minus, minus, plus, plus. Next two would be minus, minus. It's going to keep going on. So that's not negative 1 to the n. It's not negative 1 to the 2n plus 1 or 2n or any of that. I'm just going to tell you what this is, and we can verify it. You get alternating signs like that, where it starts off positive, then goes negative, negative, positive, positive. It's n times n plus 1 over 2. Let's double check this, and we'll kind of see what's happening. So when we start at 0, does this work? Negative 1 to the 0 is positive 1. When you plug in 1 times 2 divided by 2, the 2's cancel out, so you just get 1. Negative 1 to the 1 is negative 1. Plug in 2. 2 times 3 divided by 2, the 2's cancel out. Negative 1 to the 3 is negative 1. One more here. Plug in 3. 3 times 4 over 2. 4 over 2 reduces. 2 times 3 is 6, so negative 1 to the 6 is positive 1, and it'll keep going. So this is not something I thought of on my own. I had looked that up at some point, or I think it might have been in our textbook. Okay, so why do I need that? Because cosine x, I'm trying to build the terms here so that I can come up with what the nth term is. So it's equal to radical 2 over 2 minus radical 2 over 2 times x minus pi over 4 to the first power minus radical 2 over 2 times x minus pi over 4 to the second power over 2 factorial. Easy to forget that. Plus radical 2 over 2 times x minus pi over 4 to the third power over 3 factorial. So what's the power series in general? We figured out the alternating piece, or I told you, I guess. It's negative 1 times n plus 1 over 2. There is a radical 2 over 2 in every single term. There's an x minus pi over 4 to the n in every term over an n factorial. Okay, not pretty. I could clean it up a little bit better, but for now I'm just going to leave it like that. And yeah, so I think that's as far as we're going to go with that. When we say centered at pi over 4, remember that's just saying the point of tangency here, rather than being at 0, it's over at pi over 4. And then the Taylor series matches up with the cosine of x on the interval of convergence, which in this case is all real numbers. All right, that's it for today.